on the top of it, if I want to use that particular many core or multi-core kind of the architecture efficiently, then what are the ways to use those hardware efficiently, as Dr. Vamsi has mentioned. So we need to use the hardware efficiently. So if we go for the tradition with the traditional languages, then there are some limitations to it, right? So in this particular session we will be talking on one of the widely used program models, which takes into account the distributed kind of system to program upon, right? So my agenda for this session is briefly we'll touch upon what exactly the HPC, and on that we'll try to have the foundation. Then we'll switch on to the massive passing interface. We'll try to understand what exactly the MPI is, and in that as well try to understand what is point to point and the collective communication route and those things. So though this as particular aspect everyone knows about it, still I just want to have a minute on it. Okay, so why exactly the need of HPC? So there are a variety of domains which are getting emerged, and where there is a requirement of high compute intensive systems, right? Starting from the climate modeling to recently the buzzword like artificial intelligence, machine learning, and there's so many, right? So for those applications and those areas of research and research and the gamings and many more things where we require systems with high compute intensive capabilities, right? And certainly when we talk about the parallel programming as in versus to a serial computing, what exactly makes the difference? If just we try to enhance the capacity of a single core system, so certainly there are multiple physical as well as some programmatical obstacles and limitations to it. So when we go for the parallel programming, it makes the life easy in all essence. So just take an example of if you visit the bank and if there is a single counter and there are hundreds of customers waiting in the queue. So you can imagine that particular system versus a same bank with multiple counters which are performing the same type of task, but those are in a parallel way. So basically in scientific and engineering domains as well, there are so many problems available which can be implemented in a parallel way, so that we will get two aspects. First one is efficiency of running those problems as well as the time gain, right? So when we try to check the what exactly the difference between our normal systems and how the HP systems looks like, basically this particular component basically is different from our normal system to the HP system. That particular component is nothing but central processing unit, right? So what exactly this central processing unit or the big HPC cluster consists of, right? So in a component wise, if we look into that particular system, so it looks something like that. We have some users who get the access of the system for the login nodes, and on the top, on the back end of it, there are so many nodes. We called it as CPU nodes as well as the GPU nodes. So and the architectures of all these nodes you have studied in the last session in a very beautiful way. Dr. Vamsi has explained it, right? So this is an generic architecture and the components of any HPC cluster looks like, right? And when we try to look for the in detail or from the backend perspective what exactly the multi-node HPC system consists of, then you can see that there are some compute nodes which are connected by some interconnect, and every compute node consists of some number of cores. So our ultimate target is to use all these cores which are connected, okay, to perform a single task of my interest. That particular application from in any domain like material science, molecular dynamics, or any area which you work. So our ultimate target is to utilize all the backend resources which are available, right? So when we try to look upon the different programming models, right? So exactly where this program model fits into, like in your current program as well, there are sessions on the OpenMP, there are sessions on the MPI, there are sessions on the CUDA. So there may be questions in the layman man, okay, or who don't know about these particular things, that why we are learning these different program models in the single program. or what is the difference between them, and in which scenario I should use them, and what is the capability of those. So if I just take a some, yeah, like sections of a bigger space systems where like there are two nodes connected with each other via some interconnect, and there is another node which is called as GPU node, which is associated with GPU card, right, like NVIDIA's Intel GPU or anything. So if I want to program a single node which is having like a shared memory kind of architecture, in that particular, like that particular system is referred as like a shared memory system. And what exactly the shared memory system, where actually all cores are there and which actually access the single unit of the memory which is available on that particular node, right? So and in order to program such particular like system, you can use a model called as the OpenMP, that's open multiprocessing. So from the back, or from the deep perspective, if you want to see what exactly the shared memory system is, so there is a one single like a main memory or RAM, and there are multiple CPUs which have the direct access of this particular system, and this is referred as the shared memory system. And if I want to program such systems, we use go for the OpenMP. Now if the system is of a distributed kind of nature, right, so it means that there are like two nodes, and these nodes are actually connected via some interconnect, okay. So this complete system, right, is referred as a distributed system, where you can see that one the memory of one single uh, a CPU is not directly accessible the memory of another CPU. If I want to access it, then I need to go via some network or a interconnect, right? So such kinds of system is referred as a distributed memory system, right? And if I want to like take the benefit of all the cores in the given system, then one need to go for program models like a message passing interface, right? Now when these systems, like when we go for the if there is a system which is having the multi-core as well as distributed kind of system on their complete whatever the architecture they have, so such kind of system is referred as the hybrid system. And if I want to use the cores within the node as well as the complete core of the system which are connected via network, then I need to use MPI plus OpenMP, and in a like a hybrid mode. So both the program models we can use to leverage the best performance out of whatever the system is available with you, right? So the hybrid kind of system has architecture like that. There are some nodes are actually connected via network, and within the node we can use shared memory systems or shared memory program models like OpenMP and M, right? And for across the nodes we can go for the MPI. So and just to touch upon like when if there is a
Sir, you are
program
muted,
that,
sir.
yes, hello.
So, sir, you are muted and your screen got disappears.
Oh, okay.
Can you please share again, sir, your slide?
uh, okay, actually I'm not muted anyway. Yeah, please let me know on which slide actually I was there. Okay, hello, is my screen visible now?
Now it's visible, sir.
Okay, so on which slide I was?
You are little far. I mean ahead.
Here.
Still moving, sir.
Okay,
Even this is
sorry.
also 10, sir.
Okay, I here?
Yes, sir.
Okay, sorry for the interruption, maybe I didn't realize it. Okay, anyway, so I hope you understood what exactly mean by of the complete HPC system is all about, right? Then like when I just take some notes, okay, from the complete cluster, okay, and I just look into, so here just take an example that okay, I have taken two nodes, okay, and when I try to look for the single node, okay, which is having like multiple cores situated on that particular system, right? So such kind of system is referred as the shared memory system. And if I want to program such kind of system, that then we use a model called as the OpenMP, where I suppose you have already been uh, taught about, right? And the basic architecture of like shared memory system is that they have the unique or one single memory, and all the cores situated on that particular system, they can have the direct access of their main memory, right? So now when we try to look for the system like where some number of nodes are connected via intermediate network like InfiniBand or like whatever the available network available with you, okay? So that particular system is somehow referred as the distributed memory systems, and if I want to program for such system, then a model called as the MPI is used. So when we look at the architecture of this particular system, okay, it looks like that, okay, yeah, there is one node, and if this particular node wants to have the access of the memory or the resources available here, they need to go via network. So such kind of system is referred as the distributed kind of system, right? And when we consider both like shared and distributed system in a single window, then that particular system is referred as the hybrid system, right? So there are nodes with multi cores, and all there are multiple nodes are connected via some internet, and if I want to program for both, then in that particular scenario we can use the MPI plus OpenMP in a hybrid mode, right? Now, just to touch upon, like if there is a GPU card attached to that particular node, and if I want to refer that particular node, then we can like consider it as accelerated computing node. Okay, this particular GPU card may be from the different vendors like NVIDIA or maybe Inter, as Dr. Vamshi has mentioned about it. Okay, so if I want to program such kind of system, then you can use the CUDA. So I hope with this you understood like whatever the program models you are going to learn in this session, okay, in this FDP program. So every model fits into what uh, scenario in complete HPC environment, right? And in this particular program, like in this particular session, we will be touching upon some of the concepts regarding the MPI, distributed memory system. So let's start to dig up some of the aspects of the message passing interface. So before proceeding further, just I want to confirm, sir, am I audible once again? And is it everything fine at your end? Is my screen and voice is clear to you? Hello, hello. Okay, thank you. So let's start with what exactly the MPI is about. Okay, so MPI is nothing but in a simple manner. Okay, if there are like different processes, okay, and if I want to send a message from one process to another process, okay, in a single like in a simple way, I can refer like message passing interface as a process where if there are like multiple cores working, okay, and if one core does some task, he wants to transfer some results or anything from to another core, then via this message passing interface we can do that particular work, right? And specifically when we talk about like message passing interface is nothing but like it's not any like IEEE or ISO standard, but it has become an industry standard, right? Industry standard means that people actually liked it and they started using it, and there are like multiple variants available in the market. So every vendor may have their own flavor of the MPI. So from the open source perspective as well, there are like variants like open MPI, MVAPitch, MPage. There are multiple standards one can use them, right? And as I had mentioned, okay, so the MPI is basically based on the routine. So what exactly the routines means, we'll try to come up in the coming slides. Okay, so before proceeding further, I have these questions for you just for your recap purpose, right? What exactly means by the process, what is the difference between the process and threads? Okay, so in OpenMP session you may have been heard about like a threads every time. So every thread is associated with underline every core. So here when I talk about the process, so here I assume that every process is like attached, or every process is referred to as one single core on that particular system, right? When I talk like a statement that I'm using the four process, it means that internally I'm using the four cores. So many people who start learning the parallel programming, they gets basically confused with the knowledge which they have in mind with their earlier experience or in their college days, like multi-processing, multi-threadings, and they try to relate those things here and they gets confused. So just a disclaimer point of like disclaimer kind of things I'm here telling you that, okay, when you are trying to learn the parallel program models like either OpenMP or MPI, and if I says that two process, then remember that those two process are referred internally for different two cores, right? So when we learn in like college days, when multiprocessing, that where in that scenario we assume that there is only one single core, and on that single core we are like rescheduling the multiple process. But here in case of the HP system or the multi-core kind of the system, we refer that if there are two process, then those two process are actually running on the different cores, okay. And here the like what is the process and difference between the process and threads, you can type into the chats, okay, the answers of this. And another question is that MPA or OpenMP a new programming language? So the answer to this question is no. Basically, the either you go for the MPA or the OpenMP, basically these are libraries or like pre-processing kinds of additional features which has been added to existing programming language like a C or Fortran, right? So basically these are the wrappers, okay, which gives the existing programming some additional capabilities to work on the multi-core kind of system. So it means that learning this language is not difficult. If you know the basic program models like a C, then you can certainly add some of the things into your current knowledge and you will be expert of this program model. So what are those concepts and what are the things, what new insights you need to have? So we'll try to talk in these sessions. So today we'll try to talk about the MPI. So in generic perspective, okay, so what is our goal is that if I have a system of multi cores, okay, multiple cores, then I want to somehow use all those cores to give a single output, right? So how I can achieve that particular goal, I will just try to create somehow some connections, okay, some communication in between this process, and I will just have the coordination and do the work. So now the question is that if I these process are there, okay, and these cores are there, how one can make the communication? So where exactly the MPI fits? So MPI fits here just to make the communication between these process. I hope you understand it. So basically how MPI works is that, let's say I have some number of cores with me, okay, and on those number of cores, basically from like compiler's perspective, it spawns some number of the that number of instance of the program, and they create something called as a communicator in between, okay. And in program it like MPI program model, we called it as a communication word, right? And synchronously they work together to give the single result for the given problem, right? So I hope you understood that. So basically, as I was mentioning about the MPA is based on the routine. So what exactly mean by routine in our simple language, okay, and in a simple sentence, if I want to tell what exactly the routine means, it is nothing but like a functions, okay. So we just call those functions, we pass some arguments to that functions, okay, and those functions has been returned their scope, okay, in some of the header files, which those header files we use in our program to get the definitions. So from the basic perspective, okay, if one knows about these basic routines like MPI initialization, communication word, communication rank, MPI send, receive and finalize, okay, one will have the fair understanding, okay, of regarding how to write an MPI program. So we'll try to look about these routines slowly in this particular session, okay. So now in a broader categories, the type of communication in case of the MPI is categorized into two. So the first one is the point to point communication and another one is the collective communication. So basically in point to point communication, At a single moment of time, there are two process involved in the communication, right? And in case of the collective communication, at a time, multiple process can communicate with each other. So that is the basic difference. So here we'll try to understand what are the routines to perform the task in both the scenarios. First, we'll try to talk about the point to point communication. So I would refer to have the real life complex problem. So by solving that particular problem, we'll try to take these routines so that you will understand two aspects. So here one aspect is like how one can apply these things to the real life problems, and in the parallelly, if one have the knowledge of that, okay, so how they can relate by solving the real life problem. So these aspects in a uh, single way we'll try to understand. Okay, so we'll just take an example of a trapezoidal rule. So many of you may be aware of what exactly the trapezoidal rule is about. So basically, trapezoidal rule calculates the area under the curve, right, by the with the help of trapeze, like this rule. So how we actually does that? If they this is, let's say this is the curve, area curve, okay, and I want to calculate the area under this curve, then I will just try to segment this curve, okay, into some trapezoids. Then we try to calculate the area of this segment, the area of this, and then we try to add those areas, individual areas, okay, to complete like approximately come up with the area under the curve, right? And this is at this side, this is the like mathematical implementation of that, right? So before proceeding further, one thing I here want to discuss with you. So either you are going for the MPI or OpenMP or any other program models like a CODA, always remember that, okay, one cannot parallelize the code, or one cannot write a parallel code if there is some dependencies available into your problem. Okay, so one will be efficiently writing the program, okay, only when if your problem possesses a nature where there is no interdependency between the like process or the in between steps, right? So just think of this particular same problem, okay, is there any dependency between the calculation of this section or calculation of this section or calculation of this section? So the answer is no, right? So I can independently calculate the area of this work. So at the same time, I can calculate the area of this work, this section, and I can calculate the area of this section. And ultimately, at the end, I can merge them. Okay, so this is a good and ideal example where we can use parallel program models, right? Then if I want to do it serially, generally what we need to do, that just this is like a simple program for it, okay, just to calculate the area under this curve. And in essence, what exactly the program does is that, so first it calculates the area of this section, then calculate the area of this section and adds to previous one, and calculate the area of this, and it will go on till all the yeah, these like trapezoidals has been covered, right? And at the end it gives the final result, right? So this is like a serial implementation of it. So if I want to do it parallelly, then as I had mentioned, okay, so I can just pass these segments to different process and then combine the results from them, and I will get the results, right? So from the theoretical perspective, this is that approach or the way we can go for it. So before like directly going to programming, so mathematically just try to uh, discrete it these workloads, okay, and every workloads we just pass on to different process, okay, and then get the work done. So what exactly we are just trying to distribute here? So if I want to do it with a single like a core or process, then from the A to B, all these values I need to pass on to and just calculate all these things. But rather than, I will try to create some local, for every process I will just segment these sections, okay, and pass these values like a, okay, to a plus n by whatever like segments we do, and we just pass on these values to this section, and all these like persons or the process will compute it differently and give back the results, right? So let's try to implement it from the start itself. So this is like a complete program, and within the program itself, as we trace it, okay, you will try to get the many things about it. So this is the simple syntax of a C program, right? So you can see that at initially we have added this standard output input output library. So this is like very first line in any C program. So there is another line here additional in our MPI program. So where we are actually adding this header mpi.h. As I had mentioned to you earlier, okay, MPI is nothing but some wrapper, okay, and there are some routines which has been declared in some header files. We are importing that, where whatever the definitions related to the MPI has been defined in that particular library, and we are just using it. That's as simple as, right? Then we have defined some of the functions to get the input from the user, and once we get, okay, so this is the function where we just pass some of the values and it will try to give the result of whatever the range we have provided to that particular function, okay, just to calculate the area under the given curve, right? And this is the function or the curve under which we are trying to calculate the area, right? And this is the snippet of the code where we are just declaring some of the values. So this is as simple as like declaring the variables. So whatever the variables we will be requiring in our program, like integers, there are some of the values declared with int, okay, some of the values with double and those things, okay. So these are some of the things which are actually same as we do in our C language. So now from here, okay, our program from the like MPI perspective starts, right? So you can you always remember that, okay, any MPI program starts with a function called as MPI init, okay, and the MPI section ends with a function called as MPI finalize. So whatever the code or whatever the functions related to MPI has to be written in these two words, so like these two functions only, MPI initialize and at the end MPI finalize. So if you try to call any functions before or after these two calls, then that particular program will not recognize it. So why? Because when I try to initialize this function or call this routine, okay, then whatever the resources required to work the MPI routines or MPI functions properly, so all those initializations will be happened with this call. So when I try to call MPI initialization, it tells that, okay, boss, there are some of the routines now, okay, coming up in the line. So for those routines I need to reserve some resources. So reserve some resources, which means that allocate some of the memory for the different variables, as we have declared some of the variables here emps status, that this variable, okay. So for such kinds of variable, space for those variables will be declared, okay, when I just call this function mpi initialization, okay. Basically this is an environment management routines which helps to initialize the required resources for the mpi routines, right? So now the very first routines, okay, which we call as mpi com rank, okay, we'll try to see what exactly this mpi com rank means. So you can just observe that this is a keyword, okay, and we are passing two arguments to here, mpi com word and mpi rank, right? So what exactly it means? So the basic syntax of this MPI com rank is that, like we called it MPI, okay, MPI com rank, and then provide the communicator and the one integer to get the value. So before that, okay, just to understand, as I had mentioned, so whenever any MPI program is run, okay, so what exactly happens that, let's say there is one simple program, so compiler try to create those many number of instances as we have mentioned the number of process. So just take an example, if I have four process, okay, and in those process, okay, if I try to run the mpi program, then mpi compiler creates the four instances of the same program, and for every instance it assigns some numbers which is called as a ranks, okay. So whenever this particular mpi com rank this routine is called, So every process gets to know that what rank has been assigned to me by my compiler. So it's same like giving a nomenclature. Okay, like just if initially when we burn, right, we any child gets burned, then we just assign some name to him. So before that, the child doesn't know what name has been given to him. Or maybe like if you are like working with some number of like students in your class, let's say in randomly you have created a group of 10 students, and you don't want to like refer them with, let's say, their original names. So what you do that you randomly assign some numbers to all the students. So like assigning the numbers to those student is a task of like a teacher. So here similar assigning the numbers to those processes is a task of compiler. But that every process also should know that okay, what number has been assigned to me. Like, yeah, as I was giving the example, like what name has been or what number has been given to every student, okay, by that particular teacher. So some knowledge and something should be there, right? So similarly here in case of the MPI programming, when this MPI com rank routine is calculated, so every process gets their own like rank. Okay, and every process have their like one keyword, one variable assigned to them, and once we called it this particular function, that particular uh, process gets to know that okay, now this is my rank. And because remember that in MPI basically on the basis of this rank the work gets distributed. It's simple as that, as professor has divided some task to 10 students, and he has told that okay, this particular chunk will be done by that particular student which is having this number. So similarly, like program it like MPI program by as well, programmer try to distribute the workload, and if that chunk of the work is identified that particular process by his rank, right? So here we got to know that okay, if this MPI com rank routine is called, okay, then every process now knows that what rank has been assigned to them by the compiler, right? Now another routine called as like a MPI com size come into the picture. So just take an example here once again. So this is simple syntax, okay, MPI com size, okay, communicator and the size. So as we have seen that now in a first case that these processes got to know that okay, I have this number assigned. Okay, now if I want to know that how many other number of peoples or how many number of process are there with whom I just need to communicate. Okay, so this particular like routine comes to picture in that scenario. So whenever this particular com size is called, then uh, these processes gets to know that every process gets to know that okay, in my communicator, okay, there are four number of process. So these two critical informations in order to like work in a group are required, right? So one thing is that what number has been assigned to me, and another thing that like with how many number of process I want to work. So in my communication word, so whatever the communication word has been declared here, how many number of other process are there. So this particular information is gathered when this particular MPI com size routine is called. So I hope you understood the basic requirement or basic functionality of these two like routines, MPI comms rank and MPI com size, right? Then just come again once with our program. Okay, now we just define it, the get date we get data from the user regarding the, as we have seen that there is a requirement of a value, b value, n, and those things, right? And then internally here we just try to calculate those things, right? In mathematical I have shown you the mathematical formula, right? Just to calculate the h, local n, and those things. So now this is the area of the code where from the programming perspective we are just dividing the work and giving the work to different process on the basis of their ranks. Okay, so here I'm just telling that for, let's say, for very first section. Okay, with that just take a bigger example that okay, the value of n is 100, value of a is from a is equal to 0 to b is equal to 100. I want to calculate the area under the curve, right? And let's say consider the number of process here as a 4. So for if we just put these values in this particular function, okay, these formulas, then I get the values of h as a 1 and local n as a 25. It means that if there are four number of process, okay, then I'm dividing the 25 chunks in the four process, and with that I'm just calculating these local a for that process p0, local b, and we are just passing those values just to calculate those. Just take an example here. If, as I had mentioned, if there are like four process and if I run the program, then four instances of the same program will be there. And for process p0, okay, the value of a will be 0 to 25. And for, because here we are just putting those values here, right? Locally a 0, it means that initially the a is 0, okay. And rank for the process p0, the rank will be 0, right? And local n as a 25 and h value 1. So, and so the value of local a is 0, and if I just try to calculate the local b, okay, so local a, so 0 plus local n multiplied by h, so 25, right? So these are the values for process p0, right? So we have told that, okay, if you have process p0, then your work of area is from 0 to 25. Similarly, for the process p1, if I just put these values in the functions, okay, value like a plus rank for the process 1 is 1, and I can get that local a is a 25 and local b is 15, 50, right? So process p1 also got the value like values from where they want to work upon. So similarly we go for the process p2, and process p2 will have 50 to 75, and process p3 will be having the values from area from 75 to 100. So this is like a simple, in a simple way we have distributed the work among the different processes, right? So now whenever like that particular program will run, so on let's say any number of process, so that particular process will first identify that, okay, my area of work is only from this range to this range, so I'm not going to bother any other range, right? And I'm working on that only. So now that particular information is with every process, right? So let's move on the next, okay, in the program. Okay, so now every process have their like data. Then here I'm just like logically I'm just trying to say that, okay, if logically I'm defining that if my area, my rank or the process p0 should receive the result from all the process, okay. And if I'm not a process p0, okay, then I'm just calculating the area, oh, okay, and I'm sharing the results. So how that particular things are happening, so here this other logic is simple, like if loop is there, okay, and we are just calculating, we are just taking the area from others and we are just adding into. So now new, these two routines are new here, okay, rather than our C program. So these two routines like MPI receive and MPI send. So what exactly these routines means, we'll try to understand, okay, in the coming slides. So remember that if you clearly understand the working of these two routines, then believe me that you will feel MPI programming as easy as any other program language. Okay, so if you just understand that, because if you understand the MPI send and receive, all other routines like the collective routines also, their functionality internally somehow they use these routines only just to efficiently do their processing. Okay, so let's try to understand these scenarios. Okay, so what first try to understand MPS send and what exactly it consists of. So practically you see, you have seen that here, okay, MPS send has this some number of like parameters we are passing to it. Okay, now what exactly those parameters is means of, like this is basic syntax of MPI send routine. Okay, so we'll just try to understand what exactly that every syntax means about. So very first parameter, okay, is nothing but address of message buffer. So like what message you want to send, okay. And then the another like parameter is like size of the message. So from these two like parameters, like that particular process understands that, okay, this is the memory, and from that this is the address of the memory, and from that, okay, this is the another location of the memory. So from these two parameters, I can calculate the size of the message to be transferred. Then third parameter says about the type of data type of that message. Either I'm going to send the some numbers, int or float or whatever the type. Okay. So these three parameters basically talks about the message to be transferred. Then fourth parameter talks about the destination process rank. So if I this is my message with these three entities, then which rank or which process I want to send. So I'm just passing, okay, a destination process rank with the fourth parameter. Then another interesting parameter like tag or message identifier. Here we have talked like with the data type, we understood that okay, this is either an int type or a float type or any other data type. Now I just want to have one message identifier as well. So if I am working on same type of data, okay, but still there are like many practical cases that I want to segregate those data as well. So the message or one additional parameter has been given to just to have the identifier or tag to that particular message. And then finally is the MPI communicator. So within that part, which what is the MPI communicator or what is the number of process within that particular, so that these informations needed while transferring the message. So you can just like relate this example with your day-to-day work scenarios. Okay, where like if you want to distribute any work, okay, if you just want to send the message to anyone, what generally process you do, you just create the message, okay, then have the we on your letterhead as well, like if you want to send someone later, so what generally things you identify, that you identify the address from to whom I should send, what is the size and all those information. So similarly from the message passing perspective as well, we identify those things, right? So the first three things tells about the information about the message, and other three parameter tells that where and how to send that particular message. I hope you understand that, right? So and when we talk about the MPI receive as well, then there are like one additional parameter is there in case of the MPI receive. You can see that MPI status. So all other parameters are like the same, but only the difference is that remember that in the MPI send we are sending something, but in case of the MPI receive we are receiving something. So it means that I should reserve some memory to take the message, right? So that's why the address of the message buffer and the size of the message bar, just declare some like bucket of the memory where I can receive the message. Okay, so I'm telling that then what type of data I'm expecting. Okay, then these first three parameters talks about it. Then another parameters like source. Okay, here we try to see that from which process I'm expecting the message, so what is the rank of that particular process. Then fifth parameter is like a tag or message identifier. Then sixth one is a communicator, and then seventh one is the it indicates that the status of received message. So it may be possibility that there is a big message, but you want to know that whether that particular message has been completely received or not. Okay, so this particular if I check, okay, this particular parameter, then I can get to know that okay, I have got the complete message, okay, the flag either 1 or 0, something like that. Okay, so this helps to tell or get the notification or information that okay, either I have received the message completely or not, something like that. So I hope you got what I'm trying to say. Okay, so this is like a basic understanding of this MPI send and receiver, like in a programming perspective. So remember that these parameters matches, okay, then you can say that okay, I'm having the proper communication. Okay, so I hope you understand that. So am I audible? I just want to have the quick confirmation. Okay, so is it everything fine? Can anyone tell me? My voice is clear and my screen is visible. Okay, thank you
Yes,
very
yes, sir.
much.
You
Yeah.
are clear, and then your it is visible, sir.
Okay, okay. Thank you. Thank you for confirmation. So let's move further. So here with programmatic in perspective, we have understood it. So let's try to understand, okay, like how basically it happens. Just try to have some visualization. If you understand that, you will be good at to go for writing the MPI program, right? So just take a scenario. What we are trying to do that, okay, let's say there is a process P0 and this is process P1. So from process P0, we are sending a message to this. So in this system, what are the things are involved? There is like called as like a system buffer, okay, where generally processor does some programming and then it stores the result to be sent to another process. Then there is a network involved, right? And here network as well, there is a called as like a network buffers, right? And from this no like process, I want to send the message to this process, okay. And this is like a generic syntax. So just take some scenario. Generally what happens that process core or process comes p0, give like prepare some result to be sent to process p1. Then he puts initially puts the message into the like the system buffer. Then the message from the system buffer is transferred to the network buffer, and from the network buffer message goes to the network buffer of the process p1, and ultimately that message goes to process p1. So this is a generic scenario happens in case of the transferring message. So on the basis of it, let's say there are like two scenarios in case of the point to point communication. One is the blocking point to point communication. So many people when they start learning this, they gets confused in what exactly the blocking, what is non blocking. They don't able to like realize what is exactly happening in case of the blocking or non-blocking, and how actually the message is getting transferred, how the message is getting received. So on that perspective we'll try to have some clarification on it. So the very first case comes into the case of the point-to-point communication is nothing but called as a blocking point-to-point communication. So what exactly happens in case of the blocking point-to-point communication? So the process p0 comes, let's say process p0 comes up with some data, and after the data is transferred to buffer, okay. So our processor waits or halts its further execution till this message is transferred to buffer, and the message is transferred from the buffer to network. Okay, so generally what happens, the process comes, he puts the data into the buffer, okay, and he the from that particular buffer the message will go to the network buffer, and till the moment this particular message is transferred to the network, then only he will come to next job. So till this particular moment, okay, he will halt himself and will not do any work. So it means that somehow he is blocking himself, okay, for that particular duration till the message is transferred to the network, okay. So whatever the then in a generic scenarios, okay, he will go here and the data will be transferred to the p0 and p0 will take. Okay, so the routines which we have seen here, okay, earlier, MPI send and receive, those were of type of blocking point to point communication type, where we have seen that there are like 6 routines in case of the MPI send and 7 routines in the MPI receive, right? So this is a case of blocking point to point communication. Another case is the non-blocking point to point communication, where you can see that the processor comes up with the data, okay, and as soon as that the data is transferred from the buffer memory to like a system buffer to network buffer, it will go for his next work, okay. So he's not waiting till the message is transferred over this network, okay. So this is actually called as scenario called as the non-blocking point-to-point communication. It means that we are very sure that okay, my network is so fast that till the moment this particular processor is coming up with new result, my data will be transferred over this network to the destination process, right? So in that scenario we use like a non-blocking point-to-point communication. So here the user or the processor is not blocking himself. So just to have divide the difference between the programmatic perspective, you can just observe that there is a brief change in the syntax. MPI I send is there, here I keyword is there, and one another additional parameter request, okay, is one another pointer is there. So why actually is required this particular parameter, I will let you know. So there may be the chances that okay, before, let's say the scenario is that in some cases, okay, your like processor has transferred the message and your network was so busy that this particular message was not transferred, and this man comes with new result, this process, okay. So maybe the possibility that as soon as it comes to this and it will try to send here, in that scenario what will happen, that earlier message will get overwritten, So here it means that we are losing some data, or maybe that particular data may be corrupted. Okay, so if I want to know, okay, whether the earlier message which is having this particular request, okay, whether that particular has been transferred over the network or not, it's just kind of an identifier you can talk. So it just tells that, okay, whether that particular message is transferred or not. So those particular things, okay, can be accomplished with the checking the taking the help of this request. So we just called a routine something called as like MPI test, okay, just to test, okay, whether that particular message has been there transferred or not. Okay, and if that particular message is still there, then we can use another routines like MPI wait till this particular request flag is like transferred or has been changed or something. So these are the scenarios. Okay, so now the question comes ki, like, when we should use for the go for the blocking, or when we should go for the non-blocking point to point communication. The answer is very simple. Okay, so if you know that, okay, you are using the very high speed network, and you know that there will be no network delay in that particular scenarios, you may prefer as like non-blocking point to point communication. But in case of non-blocking point to point communication, okay, so certainly the non-blocking point to point communication is more faster as compared to the blocking point to point communication. But there are some like scenarios where non-blocking point to point communication fails, right? Just to don't lose the data and those things. So as per your requirement and the system's availability, you can use those scenarios. So I hope you understand what exactly mean by like point to point communication, right? And when we just go through the program, okay, then it's as simple as that. We are just then printing the results, okay, whatever the results has been there, and final one routine we called, which is called as the final, okay, MPI finalize, where we just release the resources, okay, which has been created by the MPI initialize function. Okay, so you can see that whole program which we have written, okay, that is in between the MPI routines we have called in between MPI initialize and MPI finalize, right? And these are like the definitions or the functions, okay, which has been used for this particular program. Okay, so I hope you understand the basic things regarding the point to point communication. So when we try to look for the compilations and the running, when we just try to see like how we in a serial program or the C serial program, how we can compile and run it. It is as simple as like first we use the compiler, then like give the output name, and then give the program, right? And whenever this particular binary is created with this particular name, we just run it and we get the result, right? So the similarly, what is how we can do with the MPI program, there is just big difference. Like here we are using the some compiler called as GCC, here we are using the compiler called as the MPICC. So for compiling the MPI program, you need a MPI wrapper, as I have mentioned, right? So here we are using the MPI wrapper, okay, compiler, and then other things like we just provide the output, like this name, okay, binary name. And while running as well, here MPI run, you need to use this keyword MPI run hyphen NP, then specify the number of process which you want to run with, or the number of cores, and you run this particular binary, whatever the binary which have been created with the for your program, right? So this is a basic just syntax, okay. So if I the same program, if I want to run it, so this is just snippet of the program. So this was the program, okay, MPI trap. Then I compiled it, then you can see that the binary has been created, and here I have run with MPI run hyphen np4. So here I'm telling that you just use the for process. So I hope that when I compile it from the visual perspective, you know that at backend how your program was getting executed. So here this particular like command creates the four instances of this binary, right? With this mpr and hyphen np, four instances of the same program will be created at compile time, and those will be running parallelly, and whatever the task has been assigned to them, and like in between they will be communicating or transferring the results to one each other, and finally they will come up with this result, okay, with the range which we have given. So this is like a same simple syntax and simple way of working of the serial communicate, like serial uh, MPI point to point communication, or maybe the like point to point communication. Sorry, point to point communication. Right. As of now, we have tried to come up with like understood these things. Like just to have the recap: serial versus parallel approach of writing the program, MPI program. Then MPI com size, com rank. We try to understand what exactly the mean by the point to point communication, MPI send receive. So the basic understanding of these routines has been there. Okay, so if anyone having any questions regarding the point to point communication, they can put it into the chat. So later point of time, I will take into those. Okay, so or maybe I can give 1 minutes to you on that. Okay, then I will switch to impact collective communication. So is there any questions on point to point communication as of now?
So far, we have not received any questions, sir.
Okay, great.
Participants, you can just post your questions in chat box. I will be helping sir to read by reading the questions.
Yes, yes. So anyway, till the moment you will be typing, I will try to touch upon the collective communication. Okay. So in case of the collective communication, as I have mentioned, so multiple process at the same time they take part into the sending and receiving the message. Okay. So this is just a simple understanding of the collective communications. Okay. As I had mentioned, basically they involves multiple process involved in the this that communication or that message transferring. Okay, then like there are collective communication, basically we can categorize into three types basically. Okay, internally one are synchronization routines. Okay, like barriers and those things. Then another one is like called as the data movement. Okay, where we just transfer the data from one process to another process. And another thing is that like collective computation. Okay, collective computation means that we don't transfer the data, rather than we transfer the result of some operations, right? Okay, so what is those things, we'll try to understand those in coming slides. Okay, so as I had mentioned, so in case of the point to point communication, what are the basic routines? There were like two basic routines, like MPS send and communicate like receive. These are the basic two routines in case of the point to point communication. So here we'll try to understand some of the basic routines with respect to the collective communications. Okay, so if one have the good understanding of at least these routines, then they can certainly start writing the MPI program by themselves. So the very first routines, let's try to touch upon, is called as a broadcast. Okay, and this is the basic syntax of the broadcast. Okay, so where we are just mentioned telling that initially that okay, this particular data I want to broadcast means like just simply transfer the data to all process. Then here I'm telling that okay, the process, from which process I want to submit that data, and then the communicator. Just take an example: process P0 have some data with him, and he wants to send this particular data to all other process which are involved into his communicator, right? Then with this particular routine, he can directly transfer this data, right? So in the same example which we have written earlier, like we have taken into a trapezoidal rule example, where we had written very big code, a complete like if else this those many things. So basically all that particular code can be replaced with one this single line. Okay, so just if if you just want to see that particular code, okay, so you can see that. Okay, in this. Okay, so just getting the data. So all these functions, this was the big function here, right? So we had just took the data and with MPI send, okay, a b n, okay, all these values we were sending one by one. Okay, so what I mean to tell you here that okay, instead of using that, one can directly use functions, okay, like called this, like MPI send a and to all process. Because there in our example as well, one need to have the values of h, a, b and those things. So with the help of this broadcast, one can optimize their code. So you can see that in case of like point to point communication, we were like sending the message to one by one to all process. Rather than that, I'm just in a single go I will transfer the message, right? So this is the use, that was the use of the MPI broadcast. So now another routine is called as a MPI reduce. Okay, so basically here reducing means that I'm not collecting the data from any other process, rather than I'm telling that instead of sending the data, before every process do some operation on that particular data and just share me the result of that operation. So I'm not interested in the data, rather than first do some processing, like either you do some summation, either do some minimize, like minimum number, maximum number, multiplication and those things, right? So that operator we generally tells here. So we are telling that, okay, what kind of operator I want to use, like minima, maxima and those things, okay, and just do that operation and send me the result of that. So just take an example here, okay. So I'm true, telling that, okay, some values are with you, and rather than sending the data, just whatever the data which you have, just send me the result or summation of it. Okay, so this is just a simple example of the reduce. Okay, so as I had said, okay, in multiple lines in trapezoidal programs we can like, where, because there you can see that, okay, in case of the process P0, here we were every time, I will just show you that, okay, line here. Okay, that is very lengthy, then just anyway, I'm going to show you. Okay. Mm, okay, this was the code previously that only, yes. Hmm. So you can see that here the same code. Okay, here we are telling that, okay, this particular, all other process which is having the rank other than 0 should send it, and then sequentially one by one this particular MPI, this process P0 will take the result, and they will try to add or update this particular variable. Okay, so instead of doing all these this big code, like implementing this knowledge, if, else and those things, so we can replace all these lines of codes with that simple reduction operation, right, which we have been talking here. So with this is one single line, right, and here we are telling that, okay, just use this MPI sum operator and you are done with. So you can see that how actually this is very simple just to understand, and how these particular routines also helps you to optimize your program. Then another routine called as instead of, let's say here we have told that, okay, that this particular destination, or here in case of the already, you can see that here I'm telling that, okay, yeah, at this destination process I want the result. If I want the result of all process which are involved in my communicator, okay, then I can go for the all reduce. So here you can just see, observe the difference between reduce. It has we have mentioned the destination process. If we don't mention the destination process, okay, and just reduce like that, all other parameters are same. We have just not mentioned the destination process, it becomes the all reduce. It means that whatever the result we are expecting, that result will be there, okay, with all the process. So this is that was the same simple example of all reduce. Now takes another example where we, instead of like completely sending the message, rather than I will just send the mass, that whatever the data which has been received in a chunk format. Okay, so let's say this particular process P0 has some data. In our case as well, like in case of our trapezoid rule, there was values from 0 to 100, right? So instead of telling the data, okay, anyway, in our example, we had actually calculated the numbers. But in real life scenario, there may be the scenarios that instead of sending the complete data, I will send that, okay, this particular data should be given for the process 0, or this particular data should be given for another process. So first of all, I'll just chunk that data, and I will just share that data which has been chunked to different process. So I have just scattered the given amount of data among all the processes which are involved into my into my communicator, right? So this is a simple example of the scatter. So you can see that, okay, this is the simple syntax, okay, where we are telling that, okay, so the my source process, so my data is with this source process, okay. Then initial parameters are telling that what is the complete like type of the data, okay. Then we are sending the count, like that we are chunking it, the data into different counts. So what should be the count of data to be there, and I'm putting some count this like data with the source process as well, okay. So all these things we just try to mention here, and complete data will be transferred, right? And another, so this is about the scatter, right? So now if I want to do like reverse operation of it, so if there is a chunk of data, okay, available with all the process, and then rather than putting that data with everyone, I just need to collect that data which is in the like scattered form. So in that particular case, I can use the routine called as the MPI gather. Okay, so how MPI gather works in a simple language way, if I want to understand, it's as simple as that. So if this is the the data with every process, so when the MPI gather routine is called, so the data will be available with that particular process which we have mentioned, right? So you can, here you can see that here we mentioned the destination process. So which process I want the data, we just mention here, okay, and the data will be collected to that, okay. So this is an operation of the all gather. Similarly, as we have done with the scatter, in case of the reduce and all reduce, something like that, we can also gather the process, all the data on all processes as well, with all processes. So just take an example here. If this is when I just try to if I want to gather the data, and that data should be available with all the processes which are available in the communicator, then I can use the routine called as all gather. So what is the difference between the gather and all gather? It's as simple as that, okay. We are just using this all gather, this keyword. Here we are using the gather keyword, and here in case of the gather we were giving the destination process, so where I want to gather the data. Here in case of the all gather, we don't give the destination process. You can, here you can just see that, like specifically just for understanding purpose I have kept it blank, okay. So here, this is the basic syntax of the all gather. So as I was mentioning, so if I want have the data with all process gather data, then we can go for the all gather. Then the final routine called as the synchronization route is, so in case of the MPI, there is widely used one unique utility called as the barrier, okay. Basically barrier what does is that it halts the operations of all other processes till that particular task is complete. Let's take an example. You, if there is some number of processes are working it, and in your distributing the work, you distributed the work unevenly. It means that one process has completed the task quickly, and still other which are involved into that particular program don't proceed further all till,
Sir,
yes,
your screen got off, sir.
okay, okay, just
Um, it's 9 anyhow. So how much time it takes, sir, for you to conclude?
just 2 minutes to 5 minutes
Yes, sir.
maximum. Yes, yes. So is it screen visible now?
Yes, sir. Yes.
At what point I was there?
You are at the last synchronization.
Synchronization, okay, okay. Okay, so the last thing is that synchronization, where widely used routine called as the barrier. Okay, as I hope my voice is there. Is there? Yes, sir. Sir, hello. My voice was there.
Sir.
Yeah.
Sir, is
Okay. Anyway, once again, I will try to explain it. Okay. Uh, I suppose that my voice was not there. Uh, so I was mentioning. So the barrier is one of the routine which is widely used in case of the MPI programming for like synchronization purpose. So basically, barrier is used when, like as I was mentioning, okay, if there is a task and in that particular task multiple processes are involved, and somehow you unevenly distribute the workload, and if one process completes their task, okay, quickly, and at the same time there may be the other process which are working on their part of the work, but you have the like next statement which depends on the results of all. So if you allow that how we have completed the work, just pass that, then you, it may happen that your result may hamper, right? So if specifically you want to tell all the process that okay, don't go till, don't go beyond this particular point till other process complete their task. So in that scenario, basically the MPI barrier come into the picture. Okay, so just wait till other process, and once all other process are there, okay, then only you pass this particular point. So it's as simple as the scenario with respect to the barrier. Okay, so I hope you understood all aspects regarding the collective communication. So this is just recap, okay, where what exactly involves into the like collective communications, where we try to understand the basic functionality of the different so routines like broadcast, scatter, redo, solve, gather, okay. Then barrier as well we have seen, okay. So with this, this is the end of my session. So I hope you understood like what exactly the MPI is about, in which scenario MPI is used, okay, and when we specifically talk about the MPI, what are the different types of it, like collective point-to-point communication and collective communication, okay. So anyway, there were like much more to talk upon, but due to time constraints, certainly I need to wrap up the things in a very fast way, okay. Still I hope that some things you may have understood. So if you have any questions, we may go for the questions for next couple of minutes, other than we can stop. So this was from my side. If any question is there, I'm open for the questions.
Participants, if you have any questions, you can please post in the chat box. Thank you all. Sir, I think you have made the session very clear and understood. And then in between, you have already addressed the session, questions of participants. And let me take opportunity to close this session. Our beloved Om sir, esteemed colleagues, and my dear participants, it has been an enlightening session on MPI programming, introduction to MPI, basics of MPI programming, where syntaxes and different routines of point-to-point communication, and then the communication, and then types of communications, and also optimization techniques are extensively covered by Om sir. So with his expertise and then clarity, he has taken us through the foundational concepts and the practical aspects of the MPI programming, but he has touched upon all, even the practical aspects. And he also equipped with us with the knowledge to leverage the parallel computing effectively. The detailed explanation of communication types, optimization strategies, and bit of hands-on insights with his own examples, and highly valuable for tackling the computational challenges in various domains. On behalf of the everyone present here, and on behalf of the Chaitanya Bharati Institute of Technology and the Department of IT and the organizing committee, I extend my heartfelt gratitude to Om Jadhav sir for sharing his valuable time and expertise with us. I know, sir, you just came from the other country yesterday, and then still without any second word, you joined the session half an hour before the commencement of the actual schedule. So really grateful to you, sir. And I needless to say, you are one of the inspiration to me, and then most of the participants who know you closely. And really, you inspired, sir. And your active session laid a path for us to take up the practical sessions for tomorrow, because we have a follow-up practical session for the tomorrow, the
Okay.
first session. So
Mhm.
you laid a strong path for all of us to implement these concepts in a practical session, sir. Once again, I extend my heartfelt thanks for
Yeah.
your valuable time and
Thank you
then
very much.
patient session, sir. So really inspiring and then knowledgeable, sir. Thank you very much, and I look forward for more of these kind of enriching sessions in future, sir. So please give more time to us to learn the HPC and then take it forward. Thank
Thank
you
you.
very much, sir.
Thank you very much, sir. So I hope the things which were required I was able to deliver, and thank you very much for your valuable feedback. So I will be more than happy if on this topic, if anyone have any doubt and if they want clarity on the subject, then I will be available. So thank you very much for organizing these sessions and inviting me once again. Thank you.
Thank you, sir. We'll get back to you, sir. And the participants, I request all the participants to please give your session feedback, and we will be sharing these session feedbacks to the concerned resource persons. Uh, if anything is required to even tune for the future sessions, that will be really helpful for the resource persons as well as to the organizing committee. I know in a winter, staying up to 9 o'clock is very difficult, and everybody have to rush to the duties in the early morning again. But in spite of that, sir, your session made around 200 members, is a 190 put together here and then bit of online. So put together more than 190 participants have actively participated, sir, and they patiently listened even at the late night in winter 9 o'clock. So once again, I extend my heartfelt thanks to you, sir. And with all this, I also thank the participants for your active learning, and we'll connect again tomorrow. Good night, all.
Thank you, Om Jadhav sir, for enlightening speech, sir. Thank you, sir.
Thank you very much, sir. Thank you very much. Yeah.